In this video, we will learn about calculus with parametric curves, and we have a bunch of things to go through. We'll start with the idea of tangents. Now, recall what you have learned in previous calculus is if you have y equals f of x, then dy over dx gives the slope of the tangent line. So what is our goal? Our goal is if we have a curve in parametric form, which means x is some function of a parameter t and y is some other function of parameter t, then what is dy over dx, or the slope of the tangent line? In order to do that, we are going to make use of chain rule. So by chain rule, we have that a dy over a dt is nothing but dy over dx times dx over dt. And then rearranging this gives dy over dx equals dy over dt divided by dx over dt. Or you can think of it as f prime t over, y was g, so g prime t over f prime t. Okay, so note, as long as this derivative does not equal 0, because otherwise we would have a division by 0. So there is a neat relation here to find dy over dx. The next thing to ask is, what about the second derivative? What if I want to find d squared y over dx squared? Now note that this does not equal d squared y over dt squared divided by d squared x over dt squared. So it's not as simple as the first derivative. You cannot just take the second derivatives and replace 1 by 2. But what can be done is, remember, this is d over dx of dy over dx. Now, what is dy over dx? dy over dx itself is some function of x. So we can apply the rule above. So if we apply the rule above, what we get is, if you go up here, what is it? It's dy over dt, right? So this would be d over dt of y. Here, the role of y is being played by dy over dx. And in the denominator, it's dx over dt. So you have dx over dt. So we get two results. We get that if we have parameters, x is some function of t and y is some other function of t, then the first derivative, which is dy over dx, can be found by taking dy over dt, dividing that by dx over dt. And the second derivative, d squared y over dx squared, can be found by d over dt of dy over dx, which itself you can find from the step above here, divided by dx over dt. So these are the two main results for this particular section about tangents. So let's look at an example. Suppose we have a curve C defined by x equals a t squared and y equals t cubed minus 3t. Okay, so let's find each of these derivatives. Now, to find dy over dx, I will need to find dy over dt and dx over dt. Now dy over dt, just by polynomial rule, is 3t squared minus 3, and dx over dt, again by the polynomial rule, is 2t. So dy over dx is equal to 3t squared minus 3 divided by 2t. Now what about the second derivative? For d squared y over dx squared, I need d over dt of dy over dx divided by dx over dt. Now this is basically dy over dx. So if I am finding the derivative of 3t squared minus 3 over 2t, and the denominator I already know is 2t, so here I am going to be using the quotient rule. Okay, so as per the quotient rule, I will have a 4t squared and an f prime denominator minus an f denominator prime. And all of this is divided by 2t, so which is times over 1 over 2t. So we get a 12t squared minus 6t squared plus 18, no, that's not correct, plus 6 divided by an 8t cubed. Factoring out a 2, you get a 6t squared plus 6 divided by 8t cubed, which becomes 3t squared plus 3 divided by 4t cubed. Okay, so this is just a basic evaluation. Now, what can we do with this? What can be done with this? So for that, you have to recall what information first derivative and second derivative give us. Remember, the first derivative gives us information about increasing, right? That's if f prime is positive, decreasing if f prime is negative. It also gives us information about maximas and minimas. The second derivative gives us information about concave up or concave down. And it also gives us information about inflection points. Which means that for these problems, once you have dy over dx and d squared y over dx squared in the parametric form, you can be asked the same questions. You can be asked about maximas, minimas, increasing, decreasing, concavity, and inflection points. So that part of the problem does not change in the sense that you're still asking the same question. So let's go back to the example problem. In the example problem, we found dy over dx to be 3t squared minus 3 divided by 2t. Now, when is this 0, right? So that gives us some information about critical points. Critical points, that's when the derivative is 0 or undefined. So we have 3t squared minus 3 over 2t equals 0 when the numerator is 0, and that happens when t is 1 and t is negative 1. And it is undefined when t is 0, because that makes the denominator 0. So we go along, we mark these critical points, and then we take test points on each of the intervals formed, and we find out what is the sign of this expression for each test points. So 3 times 4 minus 3 over 2 times negative 2, that's a negative number. So it is negative over here. 3 times 1/4 minus 3 divided by negative 1, that's going to be a positive number. Similarly, 3 times 1/4 minus 3 divided by positive 1 is going to be a negative number. And 3 times 4 minus 3 divided by 2 times 2 is going to be a positive number. So we have negative, positive, negative, positive. Now, remember, what this means is there's an increasing, it's decreasing, it's increasing. At 0, after 0 is decreasing, but remember 0 cannot be a max or min because it makes the slope of the tangent infinite. So it's an asymptote area. Similarly, we can do the same analysis with this dx squared over, the second derivative, which we found was 3t squared over 3 plus divided by 4t cubed. Now here, note that the numerator is always positive. Why? Because 3 and something squared plus 3 is always greater than 0. Because you're squaring, you can never get negative numbers. So the only inflection point, or the only possible inflection point, is t equals 0, which makes the denominator undefined. So if I take test points negative 1, I know my denominator is positive. 4 times negative 1 cubed is going to be a negative number. So negative here. And if I take 1, then again positive, and 4 times 1 cubed is going to be a positive number. So what I have here is I have a concave down and a concave up situation, and there is an inflection point here. Okay, so what's happening at this point, this 0 point, is there is an infinite tangent and there is an inflection point. So let's see what the curve might be doing, right? So we have x equals t squared, we have y equals t cubed minus 3t, then we have at 0, the tangent has a slope of infinity, which means the curve is doing this. It is also changing from being concave down to being concave up. So it's concave down here and it's concave up over here. Now, what about maximas and minimas? We saw there was if you're decreasing and increasing, that's a minima at negative 1. And if you are decreasing and increasing, you have another minimum, right? So you have basically a point where your tangent, the slope of your tangent becomes 0. So more details about how this curve was formed will be discussed later. But the basic idea is that over here you have a flat tangent, over here you have a flat tangent, over here you have a vertical tangent. So that's it for this particular video.